So we in your programs, ICT program, you will take 2 courses, computer architecture and computer system, and you should study computer architecture before you take this course, computer system. So if anyone here did not study computer architecture in advance, I think you may cancel this course, because you should study computer architecture before. So the knowledge in these 2 courses are related to each other, and if not, you still okay to register this course, but you may have difficulty to understand the knowledge. Is there anyone in this situation have not studied computer architecture yet? Okay, maybe not. So depend on you, and you should consider about that problem. And okay, I will first I will introduce briefly information. I uploaded the materials in here in the 5 folders, so you can download the slide, the lecture slide in here, and there are 3 main topics in this course, computer system. There are 3 chapters according to the reference textbook from chapter 5 about memory hierarchies, chapter 6 about storage and other I/O topics, and chapter 7 about multi-core, multi-processor, and multi-and cluster. And the slide it comes from the textbook computer organization and design, and there I upload 2 versions here, the 4th edition and the newer one, 5th edition, published in 2014. And this textbook is very famous, you know, by publisher MK and by the authors David Pattison and John Hennessy. From page, no need. So if you search the internet about the John Hennessy's John Hennessy Stanford. Yeah, he is the author of this famous textbook, He is president of Stanford University, and he a leader of the research group to design the MIPS MIPS processor. His stories. Yeah, this MIPS architecture designed by the group from the Stanford and then become to the commercial product by the company MIPS technology and imagination technologies. So I show some information to prove that the textbook is very famous in the world, and it used to the education in many universities, including Stanford Uni here. And we also use this material for our course. And there are 3 chapters, 5, 6, 7 in the code computer system. Okay, you can download the textbook in here, both version, the 4th version and the 5th version. So there are some update information in newer version, but the slide refer to the 4th edition. Okay, so back to the content of this course. You will study 3 main topics about the memory hierarchy, storage, and advanced microprocessor parallel system in the chapter 7. And you also have examination, like other course. So the midterm examination and the final examination will be held maybe online exam or offline exam, depend on the situation. So we hope we can go to the campus and study on the classroom in our school. But we now study in the Microsoft team, and today we will start from the first lesson of the chapter 5 about the memory hierarchy. So before starting, do you have any question or feedback for me? Okay, if not, so I will start from the content, the list of content we will study in the chapter 5. So you see here's quite a lot subtopic of this chapter. Some are quite long and we will take much time to go through, but some sections are very short, quite short. And so let's read the menu and imagine what you want to study in chapter 5. Maybe some part I will so briefly explain briefly. Some part, some section we will explain, we will explore detail or deeply, and some other maybe we can refer to the textbook. So you see the first introduction we will so today, and then memory technologies. So we know the hierarchies, some level of memory in the computer system, and we will start from the top level, that is the cache memory, with some basic principle of cache memory, and more deeply exploring about the measuring and improving the cache performance. Then move to the next level, virtual memory mechanism, which is used for main memory, and yeah, talk about the common framework of the memory hierarchy. Then the virtual machine, and back to the cache by cache control using finite state machine, the cache coherent problem, and yeah, some others small section, the real stuff, some peaceful or fallacy in cache level, and yeah, summarize of the chapter. Okay, and let's start from the first section, introduction. So you already knew the structure of computer, and in this diagram show the 5 classical components of a computer. We understand the mechanism of the computer. That is the processor run a program loaded into main memory. So CPUs or processor fetch instruction from main memory, fetch instruction and data from main memory, and execute the instruction, process the data, yeah, by using the control unit and data part. And yeah, so processor need to read and write main memory, access main memory, and also communicate with peripherals devices. So get input data from the outside and output the data, interact with the user or real world. So that we already know about the component of computer and its role or function. And let's see, you study about processor in previous course, computer architecture. And in this course, we consider about the main memory system and input-output system. So for memory in computer system, so we have some level of memory, and we call that the memory hierarchies. And this diagram shows the basic structure of a memory hierarchies. Yeah. So the top level is processor. We use register inside processor to store temporary information. So there are also the top level of the memory in computer system, and processor communicate with main memory or RAM, ROM RAM. There's one buffer between them. So we use cache memory to buffer for accessing main memory from CPU, from processor, and the bottom one is peripherals storage. So they are disks, ATD, SSD. So in the hierarchies, we consider some characteristics about speed, size, cost, and technology. So let's see speed. So we know that from top to bottom, the speed decrease. The speed of processor is the fastest, or cache memory attached to processor, the fastest one. CPU access the data from cache memory nearby is very fast, but access to the main memory slower, and external store memory like disk is very slow compared to the processor speed. And about size or capacity, so we know that from top to bottom the capacity of devices or memory are increasing. From smallest one, cache memory about megabyte or 100 kilobyte, several kilobyte, but RAM about 8 gigabyte, 16 gigabyte, and external memory like SSD, HDD about terabyte, 100 gigabyte, terabyte. And cost or price per bit information. So the cache memory attached to processor, the cost is very high, the highest one. The main memory or RAM, reasonable price, and external memory is the lowest memory in this hierarchy. It's quite cheap compared to the other memory level. And about the technologies, we have some technology here for cache memory using SRAM, the main memory using DRAMs, and external memory using flash technology or magnetics technologies. So that is some basics information about the memory system, and compare the technologies of this memory hierarchy. The fastest one is the SRAM for cache memory. Yeah, very fast. Access time about nanosecond, several nanosecond, but the cost very expensive. And dynamic RAM or DRAM, also fast, but slower than SRAM, than cache, faster than external storage. The price is reasonable, not so expensive, but it's not cheap compared to external memory. So magnetic disk is very slow compared to upper level. It's slow. Nowadays, if you use the computer with hard HDD, so the access time is slow compared to the other component of the system, but it's cheap. Yeah, it's cheap and it very large capacity. So we want to have ideas memory with the access time like SRAM and capacity and cost per gigabyte like magnetic disk. However, we can not do that for own memory level in the system. The engineer makes the trade-off or balance between the cost, the performance of the memory. So that's the reason why they design some level of memory in the system. And we can do that thanks to the principle of locality. So what is the principle of locality? Let's see here. Programs access a small proportion of their address space at any time. Yeah. So to run a program in RAM, the program, the instruction loaded into RAM, the address space, and processor fetch instruction, read-write data there randomly, depend on the short code, depends on the algorithm of programs. So, but in a short time, programs will access a small proportion of the memory location, or we say the address space of memory. And that is the locality. And the principle of locality may consider into two aspects, two factors. The first is the temporal locality, and the second one is the spatial locality. The temporal locality, the items accessed recently are likely to be accessed again soon. So let's see example. We have a program with instruction in a loop. Instruction in a loop like a for, a while, do while loop. So the instruction inside the loop will be repeat again and again. And so when the processor fetch the instruction from main memory, it will access to that area again and again. Okay. And for the second factors of spatial locality, said that the item near Joe's accessed recently are likely to be accessed soon. For example, let's consider sequential instructions as set or the array data. So when CPU run a program with a list of instructions like instruction 1, 2, 3, 4, 5, so on, or a set to the elements of array 0, 1, 2, 3, 4, 5. So after read instruction 1, it will fetch instruction 2, then instruction 3, or after read array element 1, 2, 3 again. Yeah. So we call that is a spatial localities. Processor will access the item near the item accessed recently. Okay, so thanks to the principle of locality, we can design the memory hierarchies. So we divide the memory into some level: cache memory, main memory, disk, and we can store everything on disk. We store a lot of data on disk storage. For example, we can store the movie, the video file, maybe very large, 20 gigabyte, 80 movie, or 30 gigabyte example. And if we want to access that amount of data, we run a program to load the data into the RAM. For example, you run media player to play a movie, 20 gigabyte. So how processor do that? How computer do that? Now run a program media player, load the program into the RAM, load the data file, the data into RAM, but we could not load all data. The data is very large. Maybe the main memory only 8 gigabyte RAM, was 4 gigabytes. So the program copy a proportion of the data from disk, recently accessed items or nearby items from disk to smaller DRAM memory or main memory. So main memory play a role like buffer for disk. Okay, and in upper level, when the processor fetch the data from main memory or fetch the instruction from main memory to CPU to execute. So it does not copy all, it copy recently accessed items or nearby item from DRAM to smaller SRAM memory. from main memory to cache memory, and cache memory attached to the CPU. Yeah. So cache memory and CPU like inside the microprocessor chip. Let's see this picture. Show the memory hierarchies in simplified way. In the top pyramid, we have the CPUs, processor. This is the processor chip, and CPUs. We have the register inside CPU. Register store the temporary information, store the information for the operating of the CPU. And this component is very fast, but super expensive and tiny capacity. And processor or CPU accept physical memory. So it uses the buffer between the CPU and physical memory, and we call that is the cache memory. So next level is the CPU cache. CPU cache memory is also fast. But expensive and small capacities. And for next level physical memory, we did it RAM. We have some type of technology for RAM here, and it's also fast, priced reasonably, and average capacity, for example 8 GB. Yeah. And solid state memory next level is external memory with average speed, price also there is reasonably, and average capacity. The bottom one is the mechanical hard drive. So we store, this is the external storage to store the data. We call that a file-based memory. It's slow but cheap and large capacity. And we use a virtual memory like a buffer for the storage to access to the storage or disk. Okay, so here is the memory hierarchy in the computer system, and we will go through each level from the cache memory, of physical and virtual memory in a later session. But before to move next section, we should understand the terms in memory hierarchy levels. Here. So let's see the diagram in the left. We have the processor. Processors access to the we have two levels here, and one is the upper level of memory and one is a lower level. So in general, we call that is the upper level and lower level, but in some specific situation, we will have, for example, cache memory and main memory. But the other context, we may have main memory and disk storage. They are some level in memory hierarchy, which is upper one and lower one. Okay, and here we have the concept to you for main memory and cache. We call block or like. Block or line. They are unit of copying data. So you see the picture, so the block, a box, a square box, the blue one here. They are a block or line. They are same things, but block we use for main memory and line we use for cache memory. One block may contain multiple words. So block size may be 8, 1 word, 2 word, 4 words, so on. And remember that one word is 4 byte or 32 bit. That is a unit of data to transfer, to copy between two levels of memory, so upper one and lower one. And now processors access the data in main memory, lower level. But firstly, processor will search the data in cache memory, nearby processor, attack to processor. So if the access data is present in cache or in upper level, so we call that situation it hit situation, hit case. Yeah, hit means the access certified by upper level. So the data is available in upper level. The expected data, the desired data available there in upper level. So that is the hit case. If not, otherwise, if access data is not present or it's absent, so we call that is a miss situation. Processor wants the data, but the data is not available in cache. So in that case, processor must access to the lower level, access to the main memory in this example. And that situation we call the missed case, hit and miss. And we compute the ratio of hit time and miss time. The hit ratio equal to number of hit time per the total number of assets. And miss ratio equal to number of misses per the number of assets. And of course, hit ratio and miss ratio, the sum of hit and miss ratio equal to 1. So miss ratio equal 1 minus hit ratio. For example, total is 100 accesses, and the number of hits is 90. The number of miss is 10. So hit ratio is 90%. Miss ratio is 10%. And when miss occurs, processor merge a set to the main memory to copy the data from main memory to cache. Copy one block from lower level to upper level, and it takes time. It takes long time compared to the access time to cache memory. So that time we call it a miss penalty. Miss penalty means the time to access main memory by processor. And of course, it's very long compared to the access time of cache memory. Cache memory attached to CPU, and for access main memory, CPU go to the main memory, outside the microprocessor chip. Okay, so miss penalty like a punishment for processor when processor is set to the main to require the data, but the data is not present in cache memory. Oh, okay. So from here you should understand these terms, this concept: block or light, hit and miss. What is hit and miss? Hit ratio, miss ratio, miss penalty. Do you understand these concepts? Give me feedback, yes or no.
Yes, Mr. Hùng. We are a little familiar with it from computer architecture.
Yeah, thank you, Lâm. Okay. I may forgot to introduce myself. My name is Hưng, Phạm Ngọc Hưng. Yeah, I'm come from computer engineering department in our school. Okay, and back to the slide. I think we can take a break now before move to the next section. So everyone, we have break time in 5 minutes. Hello. So we continue the lesson.
Yeah, let's continue it.
Yeah, thank you. And now we move to the section 2 about the memory technologies. So let's see the form primary technology listed here. And I recommend you to check the textbook about this section. Okay. We have three first one are semiconductor memory, but they are different in technology. SRAM, DRAM, flash. And the last one is the magnetic technology, which we use in HDD and magnetic tape also. So we know that DRAM invented for the RAM, main memory, by the dynamic RAMs, and static RAMs invented for the cache memory. Yeah, the reason why the DRAM is cheaper because DRAM uses significantly less area per bit of memory. Have flash memory. We also familiar with flash memory, which is used for SSD nowadays, so solid state drive, and USB memory drive, or SD cards, micro SD cards. DRAMs. So DRAMs organize like a matrix of column and rows, and we can access to the DRAM one location, one byte, or one series of byte in one column. In one row. One row. So we can access 1 byte or 2 byte or 4 byte or 8 byte. And this table shows the capacity of the DRAM chip and the cost per gigabyte, the access time, average access time. So in the past, it's quite information in the past, from 80th century, 80 decades to the 2012. Yeah, until nowadays, until nowadays we have DDR4, the fourth generation of DDR, double data rate DRAM, run with the 1600 megahertz clock, memory clock. Yeah. Flash memory and disk disk memory. So nowadays we replace ADD by SSD because some drawback of these technologies. This ADD very slow compared to other components, and also it makes noise and heat up the device, temperature, high temperature. Yeah, if you know, there are many plate and read-write head attached to each plate. The plate rotate around the axis and heater stick around arms. So these technologies gradually disappear, but the magnetic technology still exists for the other market, for other devices like magnetic tape, video tape, audio tape. See in cinema, or ATD still used for video recorder cameras to record a lot of data, amount of data. So we need cheap devices. We not okay. So just went through briefly about these four primary technology for memory, and now we will move to the section 3 about the first level of memory hierarchy, that is the cache memory, and we divide the into some subsections, and in here some basic of cache memory, and we will have more section about cache in later part of the lectures. Okay, and when we know the cache memory is a level of memory hierarchy closest to the CPU. So cache attached to the CPU core on microprocessor chip. So inside one chip. And let's see, assume that we have n accesses, the sequence of accesses from xn, x2 to xn minus 1, xn. And here the diagram shows the before reference to xn in the left. So CPU or processor access to the location in cache, HN, H2, H3, so on. And now CPU want to access xn location. So there's no data. So we need to copy the data from main memory to the cache. So after reference to xn, we will have the data in this location in cache. And there are some questions raised here. The first one, how do we know if the data is present is present in the cache? How do we know? How does the CPU know if the data is present? And the second one is, where does CPU look for the data? Which location CPU looking for the data? Okay, so to answer this question, we will start with one organization of cache. The simplest method to organize the cache memory, that is direct mapped cache. So we will define where or which location in cache memory to store the block data in main memory. How to determine? By using block address modulo the number of block in cache. We compute the division. Block address divide the block number in cache and get the reminder. That is the modulo. So with that method, there is only one choice, to put the block of data to cache memory. Let's see the explanation here. In the bottom, we have main memory, and in the top, we have cache memory. So assume that main memory consists of 32 blocks. 32. So we need 5 bits for addressing 32. Or block address is 5 bits. Okay, and see some example here. This block is block 1, block 0, block 1, block 2, and block 31. And block 1, the binary address is 00001. Block 29, 29, 30, 31. 29 is 11101. Okay, that is the organization of the main memory. And for cache memory, in the top, we have 8 block or 8 line in this cache. So we can use block. They are same size. Block in main memory, block in cache. 8 block in cache. And each block indexed by 3 bits. 8 blocks. So we need 3 bit indexing for each block from 0 to 7, 0, 0, 0 to 1, 1, 1. Okay, I think you will understand well this organization. And now the problem is, if we want to put one block from main memory to the location in cache, so which location we should use to store that block? We need a solution. We need to method for that problem. Store the block of data, store a block in main memory to cache. And the solution here for the direct mapped cache is by using modulo, block address modulo for the number of block in cache. So we will take the block address, divide to the number of the block 8, and we got the reminder. We get the reminder, and that is the block index in cache. For example, the block address number 1, 00001. So divide to 8, divide by 8. So the remainder is 001. So this block must store in block 001, location 001 in cache. Okay, there is only one choice, no other choice. Block 1 must be stored in location 1. Okay, and maybe other block, yeah, block 9, block 9, 01001 must be stored in location 1 because 9 modulo 8 equal 1. The remainder, yeah, the 1. Same way, yeah, the other block address 17 10001 25. Okay, so they must store in location 001. And the other block address, for example, the blue one, the blue color block. This block is number 5, address 00101, number 5. So must store in location 5 in cache 101. And also 5 here, the 11, 21, 29. No, which one? 30, 31. Yeah, 10, 29. Yeah, 29, 11101 must store. Oh, sorry, store in location 101. Okay, so that is a method for direct method. Only one choice for block from main memory to store in the location in cache by using the modulo of block address or the number of block in cache. And there is one thing here, how to compute the modulo. How? Here, the number of block in cache is 8, 2 power 3. So if we divide for 2 power 3, we just need to consider 3 low order bits. So here, actually, we don't have to execute division or modular. We just check 3 order bit. 3 low order bit, because modular for 8, 2 power, so equal 3 low order bit. 001, yeah, 101, 101. That's enough. So we will know the location index in the cache or block index in the cache. Yeah. So to answer for the question where we store the data, we store block in main memory to a location in cache. And we still need to solve other question, to answer other question. How do we know which particular block is stored in a cache location? You understand this question? You see, here we have the gray location, gray color location. So this location 001 may store block number 1 or number 9 or number 17 or number 25. So which one now stay in this location? How the CPU node which particular that location store in cache location? How? So what is the solution? Can you answer this question? Can anyone answer? It also have in slide, but if you tell the answer, so you understand how.
We can use the tag to determine it.
Yeah, but what is a tag? What does the tag store?
The bit of the address is the higher bit.
Yeah, thank you. It's correct. Yeah, because here we see we need to store the block address. We need to store this location store block address 001. Sorry, 00001 or 10001. We need to store block address. So store block address together with the data. Of course, we always store the data of the block, the value of the block, the content of the block, but we also need to store the block address together. Yeah. But yeah, we don't have to store old block address bit. Actually, we only need store high order bit. Why? We just need to store 2 high order bit here, 00 or 10 or 11 to determine which block in this location, because we already have 3 low order bit. We already have the index bit of this location, that is 001. So if we know the 2 high order bit, we can combine 00 001. So we know the block address. Okay, so that is the solution, and we store that block address, high order bit of block address, in a tag, and we call that is a tag. It's like a tag we attach to the object to determine what the object is. The object, yeah. So we use tag field, tag bit to store the block address. But understand that we just need to store high order bit because we already have low order bit by the cache location index. Okay. And next problem. What if there is no data in that location? So we need to point out this location store the block or not. Okay. How? We will use one valid bit to show that. If the valid bit equal to 1, it means the data present in that location. Otherwise, valid bit equals 0, the data is does not present in that location. Okay, it's simple. It's very simple. And for initial state, the valid bit equal to 0. So it means the cache is empty. There is no data in cache location. So the valid bit is 0, no data. All the data is the old data, weighted data. So the valid bit equals 0. Okay, so combined by using tag bit, valid bit, we can solve the problem, the question to determine which block now store in the cache location, and there is data in that location or not. So let's see the real cache in this picture. To understand, we will attach the tag bit, valid bit to the cache memory. Okay, so you see this is AMD quad-core Shanghai microprocessor, an example of microprocessor. Don't care much about the detail of the name. And there are 4 CPU core here inside this microprocessor. So multi-core, CPU core 0, 1, 2, 3. And each CPU attach a cache memory. We don't see the cache level 1 inside the, maybe inside here. But we see the level 2 and level 3. So this is the cache level 2 for core 0, cache level 2 for core 1, and same for core 2, core 3. And we have the cache level 3 for whole core inside the microprocessor. And understand that this is a layout of cache memory, and cache memory not only store the content of data, but also store the tag bit and valid bit to determine which block number or block address store in the cache location, and the expected data now present in the cache location or not. Okay. And now we we go through an example of cache organization by direct methods. The cache have 8 blocks, 1 word per 1 block. So block size 1 word 4 bytes. So total size of block is 8 multiple by 4, 32 bytes or 8 words. Okay, so described by the table here. So the column data show the 8 block, 8 rows, so 8 block of the cache. So each row is 1 word or 4 bytes. But yeah, we understand that the cache not only the data column, the cache also need attach the tag bit, the tag field attached to each row to store the high address bit of memory location, but store in cache. Remember that this is the field store in cache memory. And valid bit also. the V column is the valid bit. There's only one bit and equal to 1 or 0, or we use yes or no. Yes mean 1 and no means 0. And the first column is index. We index for the 8 block of the cards from the 0 to 7. So we use 3 bit for indexing 0 0 to 1 1 1, and we call this is the address bit of cards. The card had 8 block, and this is the address of each block in cards. Its location in cards. Okay, and in physical cards, in the right figure. And now start from the initial state. So no data in each block. The block is empty. No tag in each block, and valid bit is 0 or no. There's no data there in each location. No data. And now we mean CPU processor. CPU will accept the first word number 22 in decimal system. So the word address is 22, and in binary address it's 01001 22. Okay, and now first where processor will access to the cache memory first, but which location the CPU looking for? So by modular by number of block 8. Okay, so that is a concept, but actually CPU consider 3 low order bit. So 110. So this is the location 6 in the card. So by searching location 6 in the card, location 6 here 001. Okay, so in initial no, so there's no data in that location. So this is a miss situation. Miss occurs. So when miss occurs, CPU must access to main memory, to RAM, and copy block from RAM to cache. So copy block 10110 and store in this location. For direct method, there is only one choice. The memory 22 must store in location number 6, 110. Okay, and update the tag bit. Okay, now the tag bit update the value 10. The higher to high order bit to determine this location store the word address 10110. Okay, and also update the valid bit become 1 or yes. Yeah, now there's data present in this location, and the data is block number 22 or address 5 bit here. Okay, so do you understand how the CPU work in first access to the What address 22?
Yes, Mr. Hu.
Okay, thank you. And let's do again, but with the next word address. So access time number 2. The CPU want to read or maybe write access to the block address 26 in main memory. So 26 equal 11010. Okay, and again, CPU should look for location 2, 010 location 2 in cache memory. Yeah, sorry, location 2, but there's no data, so miss occurs. And again, CPU access to main memory location 11010 and copy the data to the location 010 in cache, and update tag bit become 11, update valid bit become yes or 1. Okay, and next 26. Next 10. So sorry, not next. So now we have 2 access time. First 22 and second 26. Again, sorry, this is the again. Okay, so if we access again 22, 26. No, sorry, let me check. 22, 26. 22, 26, then 22 again. Okay, now if CPU want to access 22 again, so 22, so CPU looking for the location 6 in cache, and check the tag bit equal the tag bit of address. So 1010, they are same. Yeah, anyway, CPU that doesn't have to check because just sorry, they have to check. Yeah, take to know the location, this block address now in this location, and check the valid bit equal to yes. So the data already in there, and this is a hit situation, his case. Okay, and similar way, if CPU access again 26, so CPU will search, look for block in location number 2, 010 in cache. Check the tag bit, so tag bit of the block address and the tag bit in cache same. So the data, derive the expected data already there. Yeah, and this is also his case. And okay, maybe time up, but I will explain briefly, and we will come back to next week. If we accept number 16, so similar way, this is a miss case 16, so search in the location 0, 0, 0, 0, and no data, so miss case, and copy the data from RAM and update the tag bit, update the valid bit, access work address 3, so check the location 3, 011, no data, so miss K, and copy from RAM, update the tag bit 00, update the valid bit, become yes, and now set again number 16, so hit case because the data already there. Okay, and maybe one more, 18. 18. So there is already the data in the location 2. Yeah, but the tag bit is different. The tag bit of number 18 is 10, but now in the location 2, the tag bit of the block 11. So not the expected one, 11, but CPU 10. So this also miss occurs, and CPU need to access RAM and copy new one, 10. Okay. So you understand the organization, a direct method cast, and we will come back this example to have more explanation in next week. Okay, everyone. Do you have any questions? Still not enough student in enough student, 57, 56. Okay, I do not check the attendance today, but so we will stop the lesson today here, and we will continue in next week. See you, everyone. I will end the meeting now.
Em chào thầy.
Goodbye, Mr. Hương.
Bye.
Bye teacher.
Bye.
Em chào thầy ạ.
See you next week. Okay, thank you.
Chào thầy.